see. Oh, looky there. I had another whole slide. I could have done it. Oh gosh. All right, so potential differences in biological systems. Yeah, so I basically just left this stuff in here because of you biologists. No, no, this is kind of interesting. It's just showing you how physics actually is involved in the body and things like that. Um, so the potential difference across a cell membrane is due to different concentrations of ions in the fluids inside and outside the cell. And so those potential differences are particularly noteworthy, it says, in nerve and muscle cells. It's just showing you that, in these nerve cells, they're going to have this high potential. It's almost, it's electricity through your body, right? And it goes from this negative potential all the way to this positive 50 difference of voltage. And it's showing again, electrocardiographs showing, whenever they're making those shapes, that's just that's a voltage, which is a change of electric potential, difference of electric potential. Okay, so the relationship between electric field and potential. So we did electric field in chapter 16, so now we're having to see the relationship between the electric field and potential. So we're going to do an example here in a minute of basically how to draw an electric field and potential sketch. So whenever you have a visual representation of electric field and potential, and then you have an equipotential surface, which has the same potential at every surface, and it gives you this picture, kind of a topographical map. So everything at those particular surfaces have that potential of, like for instance right here would have this potential of 390 volts or whatever. And this is the image that I wanted it to have given you a long time ago when it was talking about electric force as compared to electric field, and a potential as electric potential energy as to electric potential. And really all it was just saying was, for electric force, you have electric field times charge. For electric potential, you have charge times potential. Okay, and so that's the only thing is per unit charge, you're going to have those by themselves. Okay, so here's an image that is showing you equipotential surfaces. Okay, so what are the green lines? So it's a positive charge. The green lines are going out of it. The green lines are electric field lines. Okay, that should seem familiar. The purple, however, is the potential, the equipotential surfaces. And so everything on this first circle right here is 100 volts. And then if you get a little bit closer, you're at 200 volts. And then closer than that, you're getting at 300 volts. And so on. I just want you to see, I know that they make circles, but if you were to take this point right here, see how the purple and the green are perpendicular? So whenever you're going to sketch electric fields and electric potentials, you have to make sure that these lines are perpendicular to each other, okay? So they can get a little crazy looking, and I believe that your lab that you guys are having to do is going to have you do some of that sketching, and it's an electric field map, but you're also having to look at the potential energies, okay? So this is our example where it's wanting us to sketch some equipotential surfaces for 2 point charges, a positive and a negative. Okay. So, want to put that too close to the letters there. Let's see, let's go look right here. And then we'll make this one our negative. Okay, so electric field lines first. As far as positive goes, electric field's going to go away from, and it's going to go to the negative. So let's just straight to it like that. And then what was one of the rules about electric field lines? They could never cross, right? So you have to be very, particular on that, and make sure your arrow is kind of doing that. And mine are going to look kind of rough. So why am I kind of curving them out here? Well, it kind of has to do with those potentials, because remember that potential, that equipotential, has to be perpendicular at these points. Okay, and same for here. I'm going to go like that. And then you can even have some that are going like out here to something else maybe. And, didn't go to my charge there. Anyway, they kind of come in here and do that. And then, you've got these potentials still, and this one has to be perpendicular at that point. I'm terrible at making circles, but you guys kind of hopefully see the point here. So yours hopefully looks a lot better when you're drawing it than mine does. All right. So I just wonder why it's not showing you the title there. Anyway, that says potential in a uniform electric field. So in a uniform electric field, that's this image right here. The field lines are equally spaced parallel lines. Well, I couldn't do that on this one because in order to draw this circle here, I kind of had to kind of loop them out a little bit. And so since the equipotential surfaces are perpendicular, they can just be these straight lines. Now, again, if we had just one charge here and one charge here, then they would start to bulge a little bit. But this is as if they, were like a parallel plate almost, where you would have, say, multiple positive charges and multiple negative charges happening. And so anyway, these perpendicular lines right here are the equipotential surfaces. And you can see that the potential decreases from one plane to the next. So right here, remember, the farther up you are on the positive, like close to the positive plate, you're going to have this huge potential energy, which also, is analogous to the electric potential, the voltage. So you have this 3 volts. The higher you are, closer to the positive, and then you go down a little bit farther, now you're at a lower potential, and so on. Okay, and it kind of showed that, let me go back to this. See how the closer you are right here to this positive charge, it's like at 600 volts here. But the farther away that you get, so here might be your negative charge right here, you're at only 100 volts. So it decreases the closer that it gets to those negatives, or farther away it gets from the positive. So since the spacing of the equipotential planes depends on the energy or the electric field in a uniform field planes, they are equal increments. All right. So I think I have some stuff for you to write now. So in order to find quantitative relationships between the field and the equipotential, we have some equations here. All right, so work is equal to force times distance. And I put an E because, obviously we're in electricity, so the electric force times distance. And electric force can also be Q times electric field, because we're trying to see the relationship between potential and electric field. So this involves electric field, and we have to include our distance still. Okay, so this equation right here is this. We had that in chapter 16. Okay, so now we're saying if you use that from chapter 16 and now you include distance, then you're dealing with work, which is electric potential energy. Okay. And so we'll go ahead and write that. So the change of electric potential energy, sorry, I wrote that E too big, is equal to negative work. So you end up getting this negative Q or charge times electric field. I'm going to go ahead and write a little vector symbol over it, times distance. Okay, we can go further even into the relationship between the electric field and the potential. So we've got our potential, which is voltage, is equal to the change of the potential energy over charge. So we just said that if you look back on the previous slide, that the potential energy was equal to negative Q times the electric field times distance. And you got to still divide it by this Q right here. So these end up canceling. So voltage is equal to negative electric field times distance. Okay? And so we, in chapter 16, we were seeing that electric field was given in units of Newton per Coulomb, where here it can also be written as volts per meter. Okay? So just something to kind of remember here. And 1 Newton per Coulomb is equal to 1 volt per meter. Alrighty. I think that's all you need for that one. And then finally, we're getting into conservation of energy for moving charges. So I'm going to stop the video since this is a new section and just start